So let's do a review of some of the organic families that we have covered so far while my dog barks in the background. Let's start. I have the organic families that we've kind of identified so far, and let's start with just their kind of basic general formula, just in general what they're like. So our alkanes are our saturated hydrocarbons. So we got hydrogens, and then this could be on more carbons, or this could also just be a hydrogen, and that would be our simplest. Our alkenes are those that contain a double bond, so we have that general formula. Our alkynes contain a triple bond, so we have that general formula of an alkyne, and I'm doing structural formulas here. You'd want to be able to recognize these in line formula as well. Our alcohols, the OH of our alcohol. You can see there's an OH right there. That can kind of help if you're having any trouble remembering that. Our ethers have this general structure. I kind of shared with you, I think, ether bunny, and then I envision those lone pairs as ears. These two R groups do need to be carbons. They can't be hydrogens, or if this is a hydrogen, we have an alcohol. So these do need to be alkyl, this ether or group. Or phenols, we have to have a benzene ring, which we can draw as alternating double bonds, or we can draw as a circle, and then we have a hydroxyl group off of it. We might also have other things, that can be substituted on it, but that's like the base group of our phenols. Thiols look a lot like alcohols in that we have some type of alkyl group that is attached to a sulfur group, or a sulfur atom that is bonded to a hydrogen. So very similar looking to our alcohol group. And then our aldehydes, so I'm going to kind of go through these last three, aldehydes, ketones, and carboxylic acids, in kind of a similar fashion, like kind of all at once and then go back, because all three of them are characterized as having a carbonyl group, a carbon double bonded to an oxygen. So that's kind of critical to recognize that they all have that carbonyl group. It's what's attached to the carbonyl group that distinguishes them. For an aldehyde, we have at least on one side, maybe even on the other for like our simplest, so we'll just put R. We have to have a hydrogen, so that means it ends there, it's terminal. So a way to memorize that is aldehyde is the only one of those three that has an H in its name, so it's the one with an H on it. The ketone, on both sides, we have specifically carbons, kind of like here with the ethers. Neither of these could be hydrogens, or we're automatically in a different group. So these have to be alkyl. These have to be carbon groups. So they're very similar, except the carbonyl group ends up being more in the middle. So something like that, as opposed to something like this, where the carbonyl group is on the end and the hydrogen's implied. And the carboxylic acid has specifically a hydroxyl group off of it. And so that's then the difference. I kind of think of, I have doing mental image of a key for this. There's the whole, I think I showed you the picture of that in the videos, so that's kind of a little memory tip. And this might not make a lot of sense right now, but the acidic nature of this hydroxyl group helps me remember that it has the hydroxyl group. We haven't learned too much about carboxylic acids yet. That's kind of why I put them in parentheses, because we are going to explore them in our next unit, learning about naming and their chemistry. But because an aldehyde or even an alcohol can be oxidized to a carboxylic acid, we do need to be familiar with their general structure. So if I'm given an aldehyde and asked to oxidize it, I need to understand how to turn that structure into a carboxylic acid, which really ends up being just changing the H to an OH. So now that we've kind of just gone through reviewing their general structure, which we want to be able to do, maybe we should even add, let's look at line formulas real quick. There we have a trans. We could also see a cis. The line formulas these are kind of strange with the triple bond. For these, there's a line formula example for an ether. Might look like this. Doesn't have to be. It could be cyclic. There's lots of other ways. These are just examples. That's kind of already a line formula, but we'll do an alternative one. We could also, could look like that as well. For these, it's going to look again, it's a lot like our alcohols. And I already did the aldehyde and ketone line formula. And let's throw on a carboxylic acid line formula as well. So there would be a carboxylic acid, where instead of ending in an alkyl group, we end in a hydroxyl group. Okay, so now let's, because we want to be able to review these, we want to be able to recognize them in structures, we need to be aware of their general formulas so that if we know we're trying to make an ether in a chemical reaction, or we know we're trying to make an alcohol, we can at least have a starting spot. Let's talk names real quick, and let's do that. We'll just do it by using a specific example of maybe the simplest one. So our simplest alkane would be a 1-carbon alkane, and it would be named methane, and that's we've learned about that in chapter 10 where we started, where if it's saturated we're going to end with that ane, and then we're identifying the number of carbons. So our simplest alkane is methane. Now our simplest alkene has to have 2 carbons, so our simplest one there is ethene. So we use the same numbering system, but we change the A to an E for that, and you can't have a methene molecule. It can't exist. So our simplest one is ethene. And then here our simplest one would be ethyne. Common name acetylene. So there's ethyne. A memory tip I saw some of you using back in Unit 1 is these follow like alphabetical. This is a single bond, a double bond, a triple bond. So like 1, 2, 3 is chronological, and A, E, Y is alphabetical. And so that can kind of be a memory tip for helping you with the names. For alcohols, our simplest one would be a 1-carbon alcohol, and we take the base name, whether that be methanol, we could have an ethenol, we could have an ether instead, so the base name of the alkyl group, and then we add OL. And there's a memory tip built in right there. We have OL in the name of the total family to tell us, to change that functional group name there at the end. Ethers, weirdest naming system possible. The simplest ether its common name would be dimethyl ether. So that would be oxygen single bonded to the simplest alkyl group on either side. So dimethyl ether, but its IUPAC name would be methoxymethane. So that's the IUPAC name. So it's a very odd one, in my opinion, where we're naming one with its kind of normal name, whether that's methanol or usually the longest carbon one, we'll get that they're the same, so it doesn't matter. It could have a double bond in there, and so we'd name it butene, and then the other is named as a methoxy. So for phenols, we're really going to name them as phenols. So we might have so our simplest one is phenol. It's already its name, right? Phenol. But we can have substituted phenols. So we can have a methylphenol. We could have a 3-ethyl phenol. We can use the orthoparameta just like we do with our benzene derivatives when they're disubstituted. So we really name it with kind of the traditional benzene rules. With our thiols, we name the R group. So our simplest one would be methane, and then we add the word thiol. I kind of like that. Methane thiol is our simplest thiol, where we just name the R group its normal name and add the word thiol at the end. We might have to locate that. This is true of a lot of these. We might have to locate depending on the size of the molecule. Locate where the hydroxyl group is. Locate which carbon on the base one that the methoxy group or the ethoxy groups stands on. So none of these are going to reflect that because we're going with the simplest. So our aldehyde, our simplest one, its IUPAC name would be methanal. And we have the AL. There's a memory tip there. AL. And the common name of that is formaldehyde. And then ketone, our simplest one, you can't have a ketone made out of 1 carbon. You can't have a ketone made out of 2 carbons. You have to, the smallest ketone possible would have to have 3 carbons. And so its IUPAC name is propanone. We replace that E with the one from the ketone naming. And it's far more often known by its common name, acetone. But propanone. And again, this is one where we might have to locate if we have a larger structure where the carbonyl carbon could be, can't be carbon 1, but it could be carbon 2 or 3 or 4, depending on the size of the structure. And then we're going to talk about naming of carboxylic acids in the future. So we'll do ... for the naming of carboxylic acids. The simplest one would be a 1 carbon 1. So just to, it's going to have something to do with meth, right? So another thing you could do, I don't have enough room for this, and I've kind of explored it a little bit in a previous video, but if you're working on some type of image like this, you could then go back and start looking at relationships between, because you're going to see that there's relationships between alcohols and ethers, and alcohols and alkanes, and alkanes and alkenes and alkanes, and then alkenes can be turned into alcohols, and alcohols can be turned into aldehydes or ketones, and ketones and aldehydes can be turned into alcohols. And exploring the interrelatedness of these different organic families can be really helpful as well.